Okay, so are we finding an answer for how many grams of sodium chloride? How many grams of sodium chloride are contained? What are you getting? You're still working? Okay, let me ask you this. What am I solving for? So I am solving for the grams, but I guess what I mean is if I have the molarity equation,
Moles.
that's right. I need to solve for the moles, right? That's my first step. Moles equals what?
0.25 times 500.
Okay, so you found the mole. You're saying you found the moles. Okay. So what does it equal in the equation? What variables? Molarity times the liters, right? So the moles equals molarity, 5.30 molar, right? Times the liters, which are 0.250 liters. Oops. And that equals the moles. And you said it was what? 1.325 moles. Okay, so now that I have the moles, what do I need to do from there? What's that?
To the grams.
Good. I need to convert from the moles to the grams. So from moles to the grams from the moles. How am I going? What numbers am I going to put in here? Moles are what? 1. Grams of moles. Moles are always 1. Okay. Grams. Where do I find that? Good. Oh, jeez. Keyboard off. Okay. So I have sodium chloride, right? Sodium from the periodic table has a mass of, let's just say 23. Chlorine, 35.5. Okay, so this is our molar mass for sodium chloride. Okay, are we okay with that? And then we're going to take 1.325 times 58.5 divided by 1, which we don't really have to do. Okay, and what do we find? What are our grams here? 77.5 grams of sodium chloride. That's how many. So practically, the reason I'd want to do this is because if I want to create a solution that is 5.3 molar, and I only want 250 milliliters of it, then I would ask the question, how much salt, how much sodium chloride do I have to dissolve into 250 milliliters to make it a 5.3 molar solution? And so then I have to calculate, okay, I need to use 77.5 grams of sodium chloride, dissolve it into 200 milliliters, and then I would dilute to 250 at the end to make sure the final volume was 250. Because once you add the water and the salt, the volume will change slightly. And so you can't just take the 77.5 grams and dissolve it directly into 250, because that'll change the volume to be greater than 250 milliliters. So you would need to put it into a smaller volume first, dissolve it, and then dilute it to 250 milliliters to have a final volume of 250. Okay, so that's practically how, in a practical way, how you would use this, right? So I want to create this solution. Okay, The typical concentration of vinegar is 0.839 molar. So that you buy vinegar at the grocery store, and that's the molarity of it. Okay, of the acid, the acetic acid in the vinegar solution. What volume of vinegar or acetic acid contains 75.6 grams of acetic acid? So, first thing, figure out the process. What is the process here that I'm following? Okay, first question. What am I solving for? Liters, right? What volume, right? What volume of vinegar? So I have the molarity equation. Okay. And I want to solve for the liters. Liters, according to the molarity equation, liters is going to equal what? Good. Moles over molarity. If you were not getting that equation, then we need to figure that out, because for this, I get all kinds of equations. I get moles times molarity. I get molarity over moles. More often than I get this equation, which is liters equals moles over molarity. Okay, so how did I get that? Well, algebraically, I just need to multiply liters to both sides to get it off the bottom, right? So I multiply liters over here. That cancels, and then I'm left with liters times molarity equals the moles. But now I need to solve for the liters. Liters, get it all by itself. That means I'm going to have to divide by molarity on both sides. Molarity cancels over here. I'm left with liters equals moles over molarity. Okay? So this is the equation that you should be getting. Okay? So molarity moves up, liters moves down. That's essentially what's happening here. And then I'm sorry. That's not what happened. Liters moves up, molarity moves down. That's what happens. Okay? And you'll have your liters solved for. So, we need to find the moles, we need to find the molarity. Did they give us the moles directly? No. So what do we have to do? 75.6 grams of acetic acid converted to the moles of acetic acid from the grams of acetic acid. We figured out the mass of acetic acid earlier. It was 60 grams per mole, right? So 60 grams for every 1 mole. 75.6 divided by 60, what do we find?
1.26.
Thank you. Grams per mole, well, we'll just say grams. Grams of acetic acid. Okay? So that's, moles, I'm confused. Moles. Okay? 1.26 moles of acetic acid. All right, that's what we're solving for. So that's going to go here in the equation, 1.26 moles. Now the molarity they gave us to be 0.839. Now with molarity, if you want to cancel your units, molarity's units are moles per liter, right? So moles per liter. So whenever you have something divided by something, then divided by again, this thing on the bottom here would actually go to the top. Okay? So it would be times liters on the top. Your moles would cancel, and you would be left with liters. So 1.26 divided by 0.839, what do we find? What is the volume here?
1.5.
1.5 liters. Okay? Is that what everybody else is getting? Okay, 1.5 liters. Which is how many milliliters? 1,500. 1,500 milliliters. Okay? So, hopefully you guys will start to see that without having to do the conversion. But if you don't, you can always do the conversion. That's fine. It'll just make it easier for you if you can. All right, so that's molarity. Now dilution plays right into molarity. So dilution allows us to run reactions at desired concentrations. So a lot of times you will make a solution that's very concentrated. It's very concentrated, and then you can keep that solution very pure, and then you can make another solution from it that's less concentrated that you can use to run all your reactions. And sometimes it gets contaminated, and you're like, oh, no big deal, I'll just make another dilution from my stock solution, they call it, the stock solution, because you keep that solution pure, and the other one you use for the dirty work. And it might get contaminated or whatever, but you're like, hey, no big deal, I'll just still go back to my stock solution. So that's where dilutions come in. right? We have to know how, or if you have a stock solution and you want to run a reaction at exact concentrations of some sort, you would dilute that stock solution to those new concentrations so that it will give you the desired reaction amounts in the reaction, okay? So dilution is very important in that way. It allows us to run reactions at the desired concentrations, okay, from our stock solutions. So when something is diluted, the grams or moles of the dissolved solute remain the same. So that's the whole idea behind dilution. So the reason this dilution equation that we're going to come up with works is because when you change the volume of something, the moles don't change. So let's say, for example, here I have 1, 2, 3, 4, 5 moles of something. Okay? I then dilute that thing. Let's say I double the volume. Okay? So it was 10 milliliters, and I took it to 20 milliliters. Now, look at the number of moles. The number of moles change? No, the number of moles remained the same, right? It remained constant. In the solution, what changed was the volume. And according to this equation, molarity equals moles over liters. Okay? The moles are constant, but did the molarity change as I changed the liters? Yes, the molarity would change, and the volume changed, right? So these two things changed, but this stayed the same. So that means I can set these two, the equations to determine these two different concentrations of these two different amounts equal to each other for the moles. So in other words, the moles of the initial solution are equal to what? The moles of the second solution, the diluted solution. What is the equation to solve for moles from the molarity equation? Moles equals what? Molarity times liters. So if the moles of 1, which is molarity of the first solution, and the liters of the solution, first solution, are equal to the moles of 2, that means that molarity of 2 and liters of 2 equals moles of 2. Okay? So this is what we've come up with. So here, this is what we're going to focus on. This is our dilution equation. Okay? M1, this is how we're going to rewrite it so that we understand it better. M1 V1 equals M2 V2. Okay? This is the dilution equation. M1 V1 equals M2 V2. The initial solution, the moles of the initial solution are equal to the moles of the second solution. Okay? Now, I changed it from liters to volume. The reason I did that is because in molarity, when we calculate molarity, it must be in units of liters. Okay, it has to be. But with this dilution equation, it doesn't. It doesn't have to be. Okay, so why is that? Well, let's consider this example up here. Okay, we have 5 moles in 10 milliliters. Okay, so what is the molarity of that, let's say? So molarity equals moles over liters. The molarity of that is 5 moles, and we had it in 10 milliliters. So it's in 0.01 liters. So 5 divided by 0.01, what is that? What is that? 500? That's very concentrated, right? Okay, that's ridiculous concentration. Okay, and then what would be the concentration of the other one in 20 milliliters? This would be 0.02. What's that?
250.
Okay, so it's 250 milliliters. Okay, which exactly should be because it's exactly half of the initial concentration. Okay, all right. So we have our two molarities. Okay, and we want to. Okay, so this is what we're going to come up with. So if I had just started with the initial solution, and I said I have a solution that it has a molarity of 500 molar times a volume of 10 liters. Let's just, oh, not 10 liters, but 0.01 liters. Okay. What will be the new molarity at the new concentration of 0.02 liters? Okay? And then we would solve it and we'd come up with what? 250, which is what we just found, right? So we would say X equals 500 times 0.01 liters divided by 0.02 liters. Now, instead of putting it in liters, what if we had left it in milliliters? Okay? Then we would say X equals 500 times 10 milliliters divided by 20 milliliters. Okay? Did you get the same answer? Yes. Why? Because this ratio, the ratio here is the same. These are exactly the same when you, so it doesn't matter whether you put it in liters or milliliters. All that matters is that you have it in the same units. Okay? It just needs to be in the same units, either liters or milliliters. Okay, so if they gave you both liters and milliliters in the question, you would have to convert one so that you could put it into the equation. Okay, so with molarity, it's very important. You have to have it in liters because you can't calculate molarity unless it's in liters. But with dilution, it can be in milliliters or liters, and you will have the exact same ratio between the liters and the milliliters. Therefore, it doesn't matter which one you use. Okay? Okay, so this is the dilution equation. That will be a reference material for you. M1V1 equals M2V2. Okay? You just simply have to know, what am I solving for? Am I solving for the initial molarity, the initial volume, the new molarity, or the new volume? Okay? So let's look at some practice here. Okay, this is just showing you dilution. So this would be a concentrated solution of copper nitrate, and then this would be the diluted solution of the copper nitrate, since you can see it's lighter in color, it's not as concentrated, right? Okay. Okay, so if 0.850 liters of a 5 molar solution of copper nitrate is diluted to a volume of 1.8 liters by the addition of water, what is the molarity of the diluted solution? I'll write down the equation for you. M1V1 equals M2V2. Okay? First thing you need to do is decide, what am I solving for in this equation? What am I solving for? Isolate that variable and then put your numbers in. Okay, so what am I solving for? M1, V1, M2, V2, what is it? M2, right? I want to know the new molarity of the new solution. So that's M2. So M2 equals, so here I can see what M2 mostly equals. M2 equals M1, V1. And then I have to get V2 over here, and I can only do that by dividing it to that other side. So M2 equals M1 V1 over V2, right? So this is the equation you should be using. The initial molarity is what? 5.00 molar. The initial volume is, okay? Now you'll notice how this is kind of in a pair in the question. A lot of times you find them in a pair like that. I'm not going to say always, but I'd say 95% of the time you find a pair, and that's your pair. Okay? You multiply those things together and you usually divide by the other thing. Okay? So this divided by 1.80 liters, which is the V2. So what is that?
I got 2.36.
2.36? 2.36 molar. Okay? That is your new molarity. Good. What volume of 0.12 molar HBr can be prepared from 11 milliliters of 0.45 molar HBr? Okay, what am I solving for? Yes, volume 2, right? V2. I want to find the volume that can be prepared. So V2 equals M1 V1 divided by M2, right? Bring M2 down here, and you get V2 all by itself. Okay, so M1, 0.12 molar. Okay. What volume? I'm sorry, that's not M1. This is. Hello. Okay, so 0.45 molar. Okay, and it's a 11 milliliters, or you could say 0.011 liters, depending on if I put it in milliliters here, my answer will be in what? If I put it in liters here, my answer will be in liters. So it just depends on what you want your answer to be. Okay, so we'll go ahead and put it in milliliters. Okay, and 0.12 molar HBr. So 0.45 times 11 divided by 0.12. What do we find?
41.25 milliliters.
Okay, so that's the volume that I would have to dilute to in order to change it from 0.45 molar to 0.12 molar. Okay? Great. 0.125 molar HNO3, nitric acid. What volume of 0.125 molar nitric acid can be prepared from 0.25 liters of 1.88 molar HNO3? So this is what we're trying to prepare, right? 0.125 molar HNO3 can be prepared from this here. Okay? Okay, what am I solving for? V2. So additional molarity 0.25. Oops, that's volume. 1.88 molar times 0.250 liters divided by 0.125. Okay, what's my liters? What is the volume that can be prepared?
3.76 liters.
Okay, so I can prepare 3.76 liters to use in this experiment. Okay? All right. What volume of 1.59 molar potassium hydroxide is required to prepare 5 liters of 0.1 molar KOH? Okay, so what am I solving for here? What's that? V1. I want to find the volume, the initial volume that would be required, right, to I want to find the initial volume of this. How much of this do I need, which is my initial molarity, to prepare that over there, right? Okay. My pen is no longer working. I think I'm out of batteries. Sure, I'll try. Thanks. Okay. If you can. Thank you. So we want to solve for V1 equals M2 V2 over M1, right? So my new molarity and volume are 5 liters and 0.1 molar. So 0.1 molar times 5.00 liters divided by M1, which is 1.59 molar KOH. Okay? And what are we finding for the initial volume?
314.
Liters?
Yes.
So I need 314 milliliters, and I would dilute it to 5 liters. Okay? And that would give me the new concentration of 0.1 molar. Okay, what volume of a 0.575 molar solution of glucose can be prepared from 50 milliliters of a 3 molar glucose solution? So M1 V1 equals M2 V2. So we're looking for V2, what volume equals M1 V1 over M2. 3.00 molar times 50.00 milliliters divided by 0.575, and that's going to give us the volume that can be prepared. Okay? All right. I don't want to belabor that too much. All right. Actually, I do want to go back to like this one really quick. So 0.314 liters is what we need to take, and we need to dilute it to 5 liters. Okay. So sometimes the question could ask, instead of what's the final volume, these are basically asking what are the initial volumes, what are the final volumes. But it could potentially ask, how much water would you need to add to dilute it to that concentration? Then what would you do? How would you determine how much water you would need to add? Well, I have my 2 volumes, right? Oh, no, this one's not. So maybe it's not the pen. What's that? Oh, there it is. Okay, here this is 5 liters, and this is 0.304 liters. So what am I starting out with? What's V1?
5. Oh, just 0.304.
I started out with 0.314, and I have to go to what? 5, right? So I'm starting out at 0.314 liters, and I have to go all the way to somewhere up here to 5 liters. So how much water would this is what I have. How much water would I add to get there?
4.6.
Okay, so I just need to take the difference between those two, right? I take the difference between those, and it tells me the amount of water that needed to be added to dilute it to that final volume. So I can't add 5 liters to 0.314, right? Otherwise that would be 5.314 liters. That would be a different molarity than the one I calculated. I have to dilute to that final volume of 5 liters, okay? So this difference would be the amount of water I would have to add, okay? All right, so just sometimes you can get questions that ask you things like that as well. So be vigilant of that. Okay, so other ways that you can calculate concentration: mass per mass percent, parts per thousand, parts per million, mass per volume percent. Okay, these are all ways that we can show concentrations within solutions. In chemistry, we use molarity most often because it relates the concentration to the moles, and we run reaction in molar amounts. And so it makes it very convenient for us to use a molar concentration of something to run a reaction in the laboratory based on those concentration units, okay? Because if it's by mass per mass, we would probably have to do some sort of conversion calculation to determine what is going to be the outcome of that, okay? But these kind of concentrations have their necessity, okay? Because if we write molar concentrations on something that we're selling at the grocery store, you know, that's not going to mean much to somebody that's reading that. So if I tell you how much sugar, how many moles of sugar are in a soft drink, then that doesn't really matter to you very much. This is the number of moles, right? But if I tell you the grams of sugar in a soft drink, then that might mean more of something to you, right? And so we want to portray those sorts of things. So when you sell something in the grocery store, it's usually by either mass per mass, most often, or it's mass per volume percents, because the layman reader will understand that better. Okay? Parts per thousand, parts per million, that's often things that are very diluted, like our drinking water, whatever is in our drinking water. It's at very dilute concentrations, and so we would want to portray them in a way that that would be reasonable. Okay, instead of having a whole bunch of 0.0000%, we make it more parts per thousand, parts per million, to portray how dilute that is. Okay. So here, liquid bleach is an aqueous solution of sodium hypochlorite. The brand has a concentration of 7.4% sodium hypochlorite by mass, or 7.4 grams of sodium hypochlorite in every 100 grams of solution. So this is a mass per mass percent solution, right? And often that's how you'll find things in the grocery store, in mass per mass. Vinegar's the same way, mass per mass percent. Okay? A 5-gram sample of spinal fluid contains 3.75 milligrams of glucose. What is the percent by mass of glucose in the spinal fluid? So mass per mass percent, mass per mass percent, you would take the mass of the solute divided by the mass of the solution and multiply it by 100. Okay? Mass of the solute. So let me see, let me go back. Okay? Mass of the solute divided by the mass of the solution times 100. Okay? So the solute here is the glucose. Okay? And we have a very small amount of glucose, 0.00375 grams. Okay, divide by the mass of the solvent, or the solution, I'm sorry, not the solvent, that's a big mistake, solution. Mass of the solute over the mass of the solution, okay, times 100. That's going to be times 100%. Okay, so we're going to have 0.00375 grams divided by 5.0 grams times 100. So what is my mass per mass percent here? Like that? 0.075, or what'd you say?
0.075.
Okay, 0.07. Thank you. Percent, right? So that's the percent I would find. Okay, so concentrated hydrochloric acid is an aqueous solution of 37.2% HCl. The density of the solution is 1.19 grams per milliliter. What mass of hydrochloric acid is contained in 5 liters of this solution? Okay, so this question is going to make you really think about all this stuff that we've been talking about. How am I going to determine the mass of hydrochloric acid in this solution? Okay, so we're going to start out. We have a percent of HCl. Okay, it's 37.2%. Whenever I have a percent, so how did I get to that percent? I got to the percent by multiplying by what? By 100. So the first thing I'd probably want to do is I'd want to get it out of percent and back to its decimal. Okay, so what is that?
0.36.
Good. So, all right. So it's 37.2%. So now we know it's 0.372 grams for every 100 grams of solution. Okay. We can assume that. Okay. Or what mass of HCl is contained in 5.5 liters. Okay, so this is in mass per mass, right? So I need to determine, I need to change. The reason they gave me the density is because I can relate the 100 grams of the solution. Let's say there's that many grams in 100 grams. I can relate it to the milliliters based on the density. Okay, so based on the density, I can change those grams down here to milliliters, and I can determine how many grams there are in how many in a certain number of milliliters. Okay, so we want to have the milliliters on the bottom. Okay, 1.19 for every 1 milliliter. Okay, because this is my density, so the grams for the milliliters. I want to get the milliliters on the bottom because I just want to take this and convert it to that, right? All right, so that's the conversion there. These grams will cancel, and I'll be left with the milliliters. Okay, because this is grams of what? Grams of solution. This is the density of the solution. So this is grams of solution also. So those will cancel. And this is grams of what? Solute. This is grams of solute. So it doesn't go there. Okay. So these will cancel, grams of solution each, and I'll be left with the milliliters on the bottom. Okay. So this is 0.372 grams times 1.19 grams of solution divided by 100 grams of solution. Those will cancel. I'll be left with grams of solute times every 1 milliliter of solution. Okay, so what is the conversion factor then? What is the ratio here of grams per milliliter? How many grams are there in every 1 milliliter of solution? 0.372 times 1.19 divided by 100. What do you find?
0.0044.
grams per milliliter, right? Or we could just write it per milliliter, like that. Okay? So how is that going to help me determine how many grams are in 500 liters, or 500 milliliters? Okay, so I start with 500 milliliters, which is 0.5 liters, right? And I'm going to use that against this conversion factor, 0.0044 grams per every 1 milliliter. Okay, so 500 times 0.004 grams will tell me how many grams are in 0.5 liters. So what did we find? 500 times 0.0044. 213. I'm sorry, what?
2.2.
Oh, 2.2. 2.213. Okay. Grams in that many milliliters. Okay? Yes, sir.
Sorry to ask, just real quick, where did you get the 100 grams from at the very beginning?
Okay, so because this was a percentage, okay, I made the assumption that there were that many there's 0.372 grams in every 100 milliliters, or every 100 grams. So I got it from that.
We have to download the browser and locker.
We need to do we're gonna do the lockdown browser. So I will give you a link to it that you can access it. Or you just use one of my computers. So it's up to you. Oh, don't forget this. Thank you. It's dead.
No, literally we just force the function right.
I was in the same thing last year.
Sim. Yeah, so yeah. Actually, part A, part B, part C.
Is that like the partial decomposition thing? No?
Yeah, if you want, I can show it to you.
And I marked you present, Mike.